Hey guys, I'm Pat Kelly. Okay, in this problem, you can see there's a lot going on. It's really a three-part problem. They give us this definite integral, and they ask us to use, for the first part, the trapezoidal rule to approximate the value of that definite integral. Second part, use Simpson rule to approximate the value of that definite integral. And I guess as a third part, they do mention to confirm your results with a graphing utility, compare your results. So make sure you have one of those handy as well. In fact, right off the bat, we're probably going to need a calculator handy, or go right to your graphing utility. Because if you're recognizing what I have written up here, as you get into either one of these rules, the trapezoidal rule or Simpson's rule, there's a lot of number crunching going on. Okay? So we want to make sure we understand how to set up the particulars for our integral into this formula, but then there's a lot of computation involved. Okay? So we'll probably resort to a calculator pretty quickly. All right, as I've been talking, then maybe you're even looking at these formulas, you have to know these or they have to be given to you. If we're going to do the trapezoidal rule, here it is. I've written it out for you. And I definitely think an important aspect of this for you is to know how to use this rule. So you got to understand the A's and the B's and all this notation. So for my given integral, they did specify that they want n equals 4. So how many little subsections they'd break that area up into. I did this ahead of time. This wasn't given to you, but your delta x is always b minus a. So 1 minus 0 in this case. 1 minus 0 is 1, and then divide by the 4. So always get a handle on your delta x, and then try to jump into the formula. So the formula for us here, for the trapezoidal rule, b minus a, again, that's 1 minus 0 is 1, divided by 2 times your n value, so we get 1 divided by 8 there. And I think for my first step filling into this formula, let's make sure we know where we're going into our function with each of these arguments. I'll make sure you know what each of the x sub whatevers is. My x sub 0, that's always going to be right where you start in your definite integral. So I'm going to need an f of 0 plus 2 times f of, and this is where your delta x kicks in. You just need to pick up from where your x value was, plus that increment in x. F of 0 plus a quarter is 1/4, right? Plus, and I'm following my formula. As you're learning this formula, the trapezoidal rule, if you're looking at coefficients, always starts with a 1, coefficient of 2, coefficient of 2, dot, dot, dot. It's always a coefficient of 2 until you get to your last term. It goes back down to a coefficient of 1. So I'm going to follow that in my work. 2 times f of, now I go back to where I was with my x, bump up by that increment. So I'm going to be looking for the f of 1/2. Plus, I'm not to the end of my interval yet, so I still have a coefficient of 2. F of, back to the half, but then increment up by a quarter, so we're going to go up to 3/4. And when I increment one last time, I'm at the end of my interval. I'm at that upper limit of integration of 1, so my coefficient goes back down to 1, and I just have f of 1. Close the square brace. Okay, good. It's always a good first step is to make sure you know how to use the formula for your given problem, your given integral. Now we have to do some plugging and chugging. You can jump to your calculator, but I think I'm going to go one step further here in my head if I can and evaluate each of these function values. So f of 0, for instance, is not bad at all, right? I haven't said it yet, so maybe I'll say it out loud in case it's not clear. In these formulas, your f of is always the integrand, right? So every time I've said f of, you're looking at this as your function. So f of 0, plug it in for x. That's why I said it wasn't bad a minute ago. F of 0 is just 1. Plus f of a quarter. Oh God, I know there's fractions, but I'm still going to try it in my head. You could grab your calculator. A quarter here squared is 1/16. I'm going to add that to 1, which would have to be 16/16. 17/16, but I'm going to flip it. I'm even going to multiply it by 2. So I'll get 32/17. Maybe you should grab a calculator and check me, okay? should be good there. Plus, putting a 1/2 in, 1/2 squared is 1/4. I've got to add that to a full 1, so 4/4. That gives me 5/4. Flip it, I'll get 4/5, but I've got to double that, so 8/5. I'm not trying to impress you with the arithmetic in my head. I just like to do it, so let me have my fun. Use your calculator if you want. F of 3/4. 3/4 is 9/16. I've got to add that to 16/16, 25/16. I'll flip that though, and I'll get 32/25. And then plus, where am I? Right there, F of 1. Plug a 1 in there, and I'm just going to get a 1/2. That was an easy one. Close my square brace. And as long as my mental arithmetic was right, those numbers should be good. But at this point, I would even go to a calculator because we want to find out what all this equals. I don't feel like getting common denominators here. We actually want to have the graphing utility handy anyway for that third part of this problem. So calculator or graphing utility, let's let that do the heavy lifting for this calculation. So I'll grab my calculator because it's handy. And I'm actually typing in 1/8 times parentheses 1 plus 32/17 plus 8/5 plus 32/25 plus 1/2 close parentheses equals, and what I'm getting here is 0.7828 if I round. 7828. As soon as I go to a calculator and as soon as I say the words round, I always feel like that should be an approximately equals, which it is actually up here. Okay, so way back up here, we are saying that our original integral approximately equals this number, the 7828 for me. Okay. Part 1, check. Part 2. Part 2 is actually doing the same thing. I mean, our goal is the same, but our method is different. We use Simpson's rule, which I've also laid out here for you. So it's, again, at first, a matter of knowing how to put the right pieces of the puzzle in the right place. So make sure this formula makes sense to you in our particular context. This will equal b over a is 1 subtract 0 again, that's 1. N is still 4, so 3 times 4, I'm getting a 1/12. And I think I'll take that same first step of just making sure I know what the arguments of my function are going to be. So x sub 0 is just 0, where you're starting in your definite integral, plus the coefficients for Simpson's rule starts with 1 and then alternates 4, 2, 4, 2, 4, 2 until you get to the last term. Coefficient goes back down to a 1. So this 4 is from the formula f of x sub 1. I do that same incrementing that I did a minute ago. Start at 0 and bump up by 1/4. So your arguments actually end up being the exact same as we did in the trapezoidal rule. So where was I in the formula? 2. F of my next argument will be 1/2 plus the formula then says 4 f of 3/4 plus, and I think I'm at the end of my interval, right? 3/4 would increment up to 1. So I'm at the end, my coefficient goes back down to 1, f of 1. And that's the formula. Okay, I've got some work to do, number crunching, but make sure that step makes sense to you in terms of how to use the formula. Definitely one of the things you're practicing in these problems is making sure you know how to apply the specific integral you're working with into the formula that you're using. Okay, so let me come down here. I would like to have some fun again, so let me try in my head some of these. F of 0, we actually already did that, right? That's 1. And in fact, f of 1/4, I'm plugging that quarter in here, and I actually already did that. That's how I got this 32/17. But that 32/17 was actually after I doubled it, so I got to be careful of that. But I'm actually doubling that to get to my 4. So this is going to be a 64/17. I'm still having some fun in my head, but you can always grab your calculator and get these numbers. Plus 2 times f of a half. I actually already did that as well. I could play around and get that number again, but it's going to be 8/5 still. Plus 4 times f of 3/4, and I've done f of 3/4 and actually multiplied by 2 already. So I just need to double this guy and get 64, 25th? And then finally, plus f of 1, which was that 1/2. Okay, make sure you agree with all those numbers. And then once you agree with those numbers, I'm going to go to my calculator again. This is more calculator gymnastics with all those fractions. So let's see what this equals. If I grab mine, and here we go. 1/12 times 1 plus 64/17 plus 8/5 plus 64/25 plus 1/2. Close the parentheses. And I'm getting a value of 0.7854 if I go to 4 decimal places again. And I round it, and it's still an approximation. I use my calculator, but I do have that addressed here, so it's only approximately equal to. Okay, so take a breath. Quick reality check is that if this is a 3-part problem, we've done the first 2 parts. Here's the definite integral. They say, please approximate the value of this definite integral using the trapezoidal rule. And that would be my answer. Second part, same integral. Approximate the value of that integral using the Simpson's rule. We did that, and that would be my answer. And before I go to the third part, I'll try to build up a little suspense here. So you notice these 2 answers are different, only a little different. And this is not necessarily a case of a homework problem asking you to do it 2 different ways to show you that, hey, no surprise, you got the same answer. These answers are just a little bit different. Pretty darn close, though. Because another point we're going to see here is that one of these is maybe a little bit better than the other. Realize big picture, these are each just an approximation to what the definite integral is. And as it turns out, one of them did a little bit better job approximating than the other. Okay, and I'm going to suggest that's why there's the third part to this problem, where what they want us to do is verify using a graphing utility. Because what we're going to see is maybe which one of these 2 values is a little bit closer to what the graphing utility tells us, okay? So grab your graphing utility. I actually still have one in hand. Go to your y equals, and you're entering that integrand expression. You've done enough of these. I hope you remember that we're plugging in this case, 1 over 1 plus x squared for a y equals. You can hit graph on that. You should see a pretty little graph. Depending what your window's set at, you might want to zoom in once to focus on the area between 0 and 1, which is what we're asked to do. But specifically what we're asked to do is to use the graphing utility's features to find this value, what the utility tells us the value is. So go to your integration capabilities, wherever they are in your graphing utility, and say a lower limit of 0, upper limit of 1. Utility has to think for a little bit. And what I'm seeing is 7854 to 4 decimal places. So that little drama that I tried to build in shows you that Simpson's rule is going to actually be a little bit more accurate than the trapezoidal rule. There's nothing wrong with the trapezoidal rule, but the Simpson's rule is going to get us a little bit better approximation to what that definite integral is going to be. Or at the very least, it's confirming what the graphing utility is saying that value is. But that's pretty darn close. Okay? All right. A lot of good work, but mostly just following the formulas and hopefully understanding what's going on, though, with those formulas. So I hope that helps. Try some more homework on your own.